Welcome to the workshop. We want to take a look at section 1.4, algorithms and their efficiency. And algorithms are really important, especially for those computer science folk. You're going to be dealing with algorithms a lot, as that's essentially what you're writing anytime you write a program. So let's take a look at our notes here. In this section, we're going to take a look at 4 different algorithms. We're going to start here with evaluating x to the power n, and then we'll look at a couple of different polynomial evaluation algorithms, and then we'll look at one more algorithm called the next subset algorithm. And the next subset algorithm kind of brings us back into section 1.3, where we were talking about the knapsack problem and having to take a look at all of the subsets of a given set. So we'll talk more about that, of course, when we get to that algorithm. All right, so let's first take a look at an algorithm for evaluating x to the power n. And to give us a little bit of an example, let's use the algorithm to evaluate. Let's go with 2 to the power 4. So in this case, x is equal to 2 and n is equal to 4 when we're evaluating x to the n. All right. So let's see here. Step 1 says that we want to let p be equal to x and k be equal to 1. So here at step 1, we would set p equal to 2 and k equal to 1. And let's see here, I want this stuff a little bit further to the right a moment. So we can discuss a little bit about what's going on as we move through the algorithm. All right, so that's step 1. Excellent. Step 2, right, it's described as the next power, which means that we're going to begin raising 2 to different powers. So this asks us to do these steps, right? We're going to do these steps while k is less than n. And in this case, right, we have n is equal to 4. So we're comparing k, which is currently 1. We're comparing it to 4. Is 1 less than n? Yes, excellent. So here in step 2, we're going to replace p with p times x. So p is now going to be equal to 2 times 2, right? Because p was 2, so 2 times 2 is 4. And then we're going to replace k with k plus 1, so k becomes 2. And then once we've completed that, we return back to the top, right? We're going to return back to here. And sorry, that's my dog that you might hear back there. Ray, are you okay there, buddy? You lay down? All right. So in step 2, we return back to the top, and certainly k, now equal to 2, is still less than 4. So we're going to continue on and repeat step 2. We're going to replace p, which is 4, with 4 times 2. So p is equal to 8, and we replace k with k plus 1. So k is equal to 3 now. And we return back to the beginning of the while. So this is called a loop. Every time we get to the bottom, we loop back to the top and we say, all right, is this condition satisfied? So while k is less than n. Let's see, now k is equal to 3. K is still less than 4, right? 3 is less than 4, so we're going to repeat it again. So step 2, again, we replace p with p times x. So we replace 8 with 8 times 2, which is 16. So p is equal to 16 now. And we increase k to 4. All right, so we've completed that. And again, we come back to the top and we see that 4 is not less than 4. So that kicks us out of the loop. So here we have 4 greater than or equal to n. Sorry, 4 greater than or equal to, let's put it this way, k greater than or equal to 4. There we go, right? We have a k value that is greater than or equal to 4, and then we leave the loop. Excellent. That's a good way to say it. So what we've done over here is we were in the while loop. So we were stuck in that loop. And this is the loop. So here's the while, here's the condition. While this is true, we do these things. And then once we get to the end while, that's what says that, you know, we do the things between while and end while. These are the two things that we did. Excellent. So from there, we move on to step 3 because we no longer have that k is less than 4. K is equal to 4, in fact, now. So we move on to step 3. And step 3, we have p is equal to 16. K is still equal to 4 because it didn't change anything there. We just output 16. Excellent. So we have we have 2 to the power 4 is equal to 16. Excellent, and that's exactly what it does for us. And we could use, right, we could do 3 to the 10th power. We just have to run through step 2 9 times instead of 3, okay? Because we run through it 1 less than the power is, right? We ran through it when k was equal to 1, when k was equal to 2, and when k was equal to 3. Once k was equal to 4, that kicked us out of the loop, and we didn't do it anymore. So excellent. So that is an algorithm for evaluating x to the n. So what we want to do is we want to evaluate the efficiency of algorithms. And the best way that we can do that is by counting the number of operations that are in it. In particular, the elementary operations. And what are the elementary operations? Well, the elementary operations are the operations that are just, let's see here, addition, subtraction, multiplication, division, or the comparison of two numbers. So how many operations were there when we computed 2 to the power 4? Well, when we evaluated 2 to the power 4, right, there was nothing done here, but when we went to step 2, there was a comparison on this line that told us to do it. So comparisons. So there was a comparison at the beginning of each loop. And there was also, so at this line, at this line, at this line, and then there was one more comparison because that's what kicked us out of the loop. So we needed the 3 comparisons that got us in the loop, and then the 1 comparison that got us out. So there were 4 comparisons. What about additions? Well, we have an addition in the loop. So there was an addition here, here, and here. So there were 3 additions. How about multiplications? Multiplications. Well, there was a multiplication in each of the times that we repeated step 2. So 1, 2, 3 multiplications as well. There were no divisions and no subtractions. So that gives us a total of 10 operations. Excellent. And then from there, so that's for x to the 4th. What about x to the n? Okay, well, we did 2 to the 4th, but what about x to the n? Well, again, right, when we did 2 to the 4th, we had to run through step 2 and 3 times, so n minus 1 times. So we're going to do for additions, we would do n minus 1 of them because we would have to increase k n minus 1 times to get it all the way to n. And multiplications, we would also do n minus 1 of those for each time that we complete step 2. Radar, that's enough. Thank you. And then let's see here, the comparisons. we would have to do, let's see, n comparisons, right? We would do a comparison at the beginning of each of step 2, which we run through n minus 1 times, and then one more an nth time to kick us out of the loop. Okay, so that's a total of n plus n minus 1 plus n minus 1 is 3n minus 2 operations. Excellent. So that is what's called the complexity of our algorithm. And so a complexity is a way of describing the efficiency of the algorithm. So again, the total number of elementary operations is called the complexity of the algorithm. And of course, it's going to depend on n. Anytime that we use it to evaluate a specific number, it would be that fixed number of operations. But the algorithm is created to take inputs. And so how many operations there are when the algorithm is executed depends on the inputs that are given to the algorithm. Okay, if we would have increased the value of n here, we would have had to run through step 2 more times. So it depends on n. So we get that our complexity, the number of elementary operations, depends on n. Excellent. All right, so for now, that's all that I wanted to share. We'll take a look at the next algorithm in the next video. So I'll see you guys back here in the workshop very shortly.